Mi nombre es Michael Idema. Puedo hablar un poco en español, pero tú no quieres oír mi español por una hora. Soy de Dakota del Sur y ahora vivo en el País Vasco, en España. Y puede ser, tengo el acento más raro en esta conferencia, pero no sé. Bueno, vamos a probar algo más en inglés. My talk is about actually building real cellular networks, not laboratory networks or experiments, but real networks that really connect people to voice services, SMS services, and data services. Going to explain what OpenBTS is, in case you have not heard of it. A very quick overview of how GSM works compared to the entire stack of GSM. I will only be talking about the radio portion of GSM, how we convert GSM into SIP, into voice over IP, the software and signaling that's available today that actually supports an architecture that OpenBTS implements, how to go from a single tower to multiple towers, so having one antenna to multiple antennas forming one logical network over a large geographic region, the APIs that we support, and then looking ahead, where can we go from here? So what is OpenBTS? It's been around since about 2007, 2008 was when it was released for the first time. It's a transparent open source gateway between cellular handsets and voice over IP networks. So if you have a voice over IP network and you put OpenBTS at the edge of it, on the other side of OpenBTS, you can connect cellular handsets. And the cellular handsets have no idea that they're speaking with a voice over IP network. The voice over IP network also has no idea that it's speaking with cellular handsets. It's an abstraction in between GSM and voice over IP. It only implements the radio interface of GSM because that's the good part, I guess. That's the most compatible part. And it implements the radio interface in C++, and that program runs in user space. This is not a custom kernel driver with a bunch of custom hardware and silicon and everything. You can run this on a virtual machine, on a Microsoft Surface tablet, and plug a radio into it, and you'll have a base station. It's very, very compatible. It uses an SDR. If you don't know what an SDR is, this is, for example, an SDR. It is a completely generic piece of hardware that sends and receives radio samples, just raw radio samples over a very large, wide spectrum. And this is the key breakthrough that makes applications like OpenBTS possible. These were only available to the military about 20 years ago for hundreds of thousands of dollars. And this is $400. So that's a major, major difference. So basically, in two pictures, OpenBTS turns this network, this is the GSM network that is in place today. It's been developed or was finalized being developed in the 80s, and it involves a whole bunch of servers, and in between every entity, there's a different protocol. All of these protocols are standardized, but usually, if you're not buying your products from the same vendor, even if they speak the same protocol, they won't work with each other. So it's like vendor lock-in through extraordinarily complex protocol design. So that's what you have. We can implement that like this, that exact same network that takes OpenBTS, puts a radio on it, the handsets still see a completely compatible GSM network. On the other side, though, you just have IP. You just have SIP, RTP. You handle register packets, invite packets, message packets. On the other side of it, a normal internet telephony service provider. We provide voice and SMS on supported radio standards. So you're not changing anything. You don't have to change the handset. The handset can be a $10, $20 feature phone that connects to these networks. We do 2G data as well. This is modem speed data, nothing spectacular, but it's enough for some basic email, WhatsApp messages without pictures, without videos, but basic texting over the top too. UMTS 3G data, we also have this. This is also open source. This was released to the public like 2 weeks ago, last week, something like that. So we have 3G data. And LTE is coming next year. So we have beacons working on LTE, but nothing more substantial. So GSM and SDRs, what are we talking about? GSM, just on the radio side, this is the hierarchy of things we'll deal with very rapidly in the next few minutes. There's towers, sectors, ARFGANs, uplink and downlink, time slots, logical channels, frames, and bursts. This is kind of the hierarchy of large to small things. Every tower can have multiple sectors. If you have one tower, it can be 360 degrees is one sector, or 3 sectors, 120-degree sectors, 4 sectors, 5 sectors. For example, in a football stadium, sometimes they have a 60-degree tower with 15 sectors in it. So they all cover, only 4 or 5 degrees each to handle 70,000 people in one section of a stadium. Those things are very impressive, by the way, to see. Sectors have multiple ARFGANs. An ARFGAN or ARFSIN is the absolute radio frequency channel number. This is actually the pair of frequencies that are being used to carry the signal. This is also why it's called carriers. I don't want to use the word carriers, though, because then you associate it with a service provider. So, yes, anyway. Each ARFGAN has 2 frequencies, uplink and downlink, the ones that actually carry the signal, and they're defined with a specific offset. Uplink and downlink have 8 time slots. So if you were into radios, that means GSM is both FDMA and TDMA, which makes it very fun to explain. Time slots have multiple logical channels. Logical channels are made of frames. Frames are made of bursts. And the bursts are the smallest thing you can talk about without talking about bits. So let's see what that actually looks like. Okay, this is going to be a little bit difficult. So there are 2 sections to this animation. The top is the downlink. This is coming from the tower to the handset. The bottom part is the uplink. Because it's very hard to scroll around, I'm just going to talk about the downlink. So across the left side here, these are your time slots. You have time slot 0 through time slot 7, and it goes and runs through these time slots top to bottom. Then it's also transmitting burst numbers across the top. Burst 0, 1, 2, 3, 4, 5. Inside these rows, these are the individual frames. So this frame is made out of 4 bursts, and they're interleaved. So if you speed this up, you see what kind of crazy... This is what's happening across the radio at about a 200 hertz rate going across the entire 8 time slots. It's reoccurring every 4 milliseconds from top to bottom. So this is what OpenBTS does, is understand these frames, understand them in the context of bursts, understands them in the combinations that they're in, the time slots they're assigned to, and the frequencies they're on. This is what OpenBTS does. And if you leave this on, it will crash the browser, because the browser's engine does not like doing that. Okay. Can't find my mouse. There it is, okay. Logical channels are divided into two groups. Broadcast, everybody can see them. If you're sitting in this room with a GSM scanner, you can decode these things. They're in plain text, so to say. You can just listen to them. There's a frequency channel that corrects the handset's radio to make sure that it's actually tuned incredibly accurately. There's a synchronization channel that just tells the handset which burst it's on as they're going from left to right in the animation. It says, I'm on burst 10 and 20 and 30 and 40. So the handset knows where to look for specific information. The broadcast channel is like an SSID in wireless networking. It says what the name of the network is, what the access parameters are, what the capabilities of the network are. Common control, this is how the network tells the handset, hey, wake up, I have to send you a text, or wake up, you're about to receive a phone call. And the inverse of that channel is the random access channel. That's how the handset asks the network for activity. Logical channels that are dedicated means there's already a handset associated with this channel. They're only talking to one handset. And it's SD, CCH, and TCH. These all have lovely names, by the way. The standalone dedicated control channel, this is signaling traffic. So this is like SIP. This is the signaling part. The standard is actually the ISDN D channel. If you know ISDN D channels, it's that standard with an M after it. And then they just cut out pieces that did not apply to wireless networks. Traffic channel is media. It's either full rate data or voice calls. So, the visualizer. This is an animation of some data coming in from our lab. And this shows an ARFGAN in the middle. It's tough to read, I'm sorry. In the middle, there's an ARFGAN. Around that ARFGAN are the time slots. Time slot 0, 1, 2, 3, 4, 5, 6, 7. And you'll see these calls being set up. They're set up on the signaling channel, and then they jump over to media, just like that. So it starts out on signaling, and then it reassociates with another time slot and jumps over there. If we wait a little bit, you'll see some more happen in the background. But that's what's happening here is calls are being set up. And this is just a visualizer of the time slot activity in OpenBTS. Yeah, so that call went away, time slot's free. Here's another call, it's getting set up, it's being associated with another time slot, moves over. That one does too, frees up the signaling channels. So you have these dedicated signaling channels and dedicated media channels. There's no real concept of concurrent signaling and media. There is one, but that's like a whole day course. So anyway. So what can we do with those? We can do normal things that we're all familiar with, but they're called, they go by different names. An LUR, MOC, MTC, lots of abbreviations. Location update, this is like a register statement. This is the handset asking for permission to use the network or telling the network where it currently is. Mobile originated call is a mobile originated call. It's you calling somebody. Mobile terminated call is the network calling you. Emergency call, this is totally cool. The emergency call in GSM is different than a mobile originated call. So when you dial 911 or 112 or 61 whatever, whatever emergency number is in your country, your phone is not actually dialing that number. When it contacts the network, it actually says, I'm making an emergency call. And the network can then destroy other channels that are open so that your emergency call can go through. This is also why your phone can make emergency calls when you do not have a SIM in it. If you dial an emergency number, it'll find whatever tower is in the area, it will associate it with it and make the call. There's a nice story from Germany. The robbers in Berlin, some thieves figured this out. So they bought a bunch of used cell phones from a used cell phone store. They bought a bunch of phones, and before they went in and robbed a bank, they dialed the emergency number on the phones, on all of the phones. And the entire tower, it canceled all the active calls. They all went away. They all filled up with emergency calls, and there's no way to prioritize one emergency call versus the other emergency call, so nobody could call the police. They got to just casually walk in and do their thing and leave, and nobody could report the crime until the phone calls stopped. So yeah, that made some networks change their access policies. Mobile originated SMS, you sending an SMS, receiving an SMS. What is an SDR? Does anybody know or have experience with SDRs? Some, yay, woohoo, SDRs. SDRs are really cool. I am not a radio guy, but I can write software. And this lets you be a radio person by just writing software. It's a completely generic radio. Before, you used to have radios for a specific purpose. You had an FM radio, or an AM radio, or a CB radio, or whatever. Now you have one radio. It's completely generic. It can send and receive samples raw, and your software is responsible for the modulation and demodulation of the samples. So if you want an FM radio, you write an FM demodulator in C++ or Python or whatever. If you want to send signals on an AM frequency, you write a modulator in Python or C++ that takes audio and turns it into amplitude modulated frames and sends them out the radio. So this is it's very fun. It's still complex because it's radio, but it's C++ or a normal language. They're differentiated by sensitivity. They have something called a noise floor. The noise floor, everything has a certain noise floor because all matter, all atoms vibrate at a certain temperature. So the only way you can make some radios more sensitive is to put them in liquid nitrogen or something like that, to actually cool them down so that the atoms vibrate slower, so that there's less noise on the channel. So that's why like deep space telescopes are liquid cooled or nitrogen cooled, so that they're incredibly sensitive. The frequency range, they're differentiated by the frequency range and the megasample bandwidth. How many samples out of this range can you get? So you may have 28 megahertz of sample range, but you can only sample at one time a little bit because the bandwidth is so low. If you have a high bandwidth, you can grab concurrent samples from the entire spectrum. You can get into this as a hobby for $25. It's very fun. SDR Sharp is the software. It runs on Windows. And this RTL SDR is a little USB SDR that plugs in. And it can, for example, this is that SDR running on, this isn't SDR Sharp, this is another program. It's similar. This is the ISM band. This is the 900 megahertz band. So you'll see like cordless telephones inside your house, or any cheap wireless electronics that use the 900 megahertz band. You see how busy it is, how much energy there is. You can highlight pieces of this and then send it through your own software to interpret it. So you can watch garage doors being opened or closed, car keyless entry systems sending signals back and forth, whatever. And if you have a lot of bandwidth, you can look at all of this stuff at the same time, which means you have multiple concurrent logical radios with one physical radio. So you don't have to have a bunch of radios. It can monitor a huge spectrum of space. This also means that moving from GSM to UMTS in your network is a software upgrade. It's just that simple. You already have the hardware that's capable of sending and receiving the samples, and to upgrade your radio access network, you just need to upgrade the software. So that is the major difference. How do we get from GSM to voice over IP? This one's easy. Mobile originated call, mobile terminated call. It's a SIP invite. I want to make a call. Depends who it's to. It looks like this. I'm not going to put you through 1,000 ladder diagrams, so don't worry, this is the only one. Between the handset and OpenBTS is a lot of traffic. It gets divided into 3 main pieces. The red is radio resource. These are all layer 3 operations in GSM. Radio resource is, I need to use this time slot, okay. Then there's mobility management. Do you actually have permission to use this time slot? Yeah, it's okay. And then the call control setup is where we actually get interested in what's going on. This is where OpenBTS needs to talk to a SIP endpoint. And these are the only things we actually convert into SIP. Everything else is abstracted by OpenBTS. So the setup gets crammed into an invite, the ringing gets converted into alerting, and the 200 OK gets converted into connecting. Mobile originated SMS and terminated SIP messages, or SIP message, all capital, SIP message packets. And location update request is a register. These both use digest authentication. So if you're familiar with how SIP uses MD5 to do a challenge response authentication, it's the same thing, except we replace the nonce with rand, which is a value that GSM specifies. We replace MD5 with the algorithm that GSM specifies. And the SRES response is also just a find and replace. I think they're closing the nightclub. Okay. So this is the only line. This is what we want to push into standardization. We want more switches to support different values for this line in SIP, where the SIP register says invite. I can see Oli shaking his head. That's not good. Theoretically, if I were to have my way, we want the algorithm to be selectable. So if a request comes in and says, I want to authenticate a handset with comp 128v1, which is a GSM standard, the switch can say, I support that, and it will do the exchange correctly. Until we have that, it's going to be tough. This is what we can capture, actually. This is this exchange. I won't go through it. My time is a little bit short. But this captures SIP packets and GSM radio frames. We have the ability to capture raw GSM radio frames and put them into Wireshark. So it's very easy to analyze. So what supports this? This is what we're trying to replace, right? This big complicated thing. Was originally replaced with this architecture, which is what we've used since the project began. We have something called central services. We use SIP-auth serve for the invite, SMQ for SMS, and asterisk for voice. It did an integration with the Kazoo project, and this is a complete integration. It looks like this. We talk to FreeSwitch over SIP. It gets converted into Erlang events that go into Kazoo and then goes out to the internet. So the interface is still the same. We're still just speaking SIP to FreeSwitch. The direct architecture, I'm working on this now. I'm trying to get more support for this in and outside of the project, just writing patches and seeing if people want to do this. You add support for the different algorithms. and you add a store and forward mechanism for SMS. This is the most difficult, biggest piece of software that would need to change. But anyway, then your architecture looks like this. You just take OpenBTS and you point the SIP proxies at asterisk or free switch or whatever, and it works. You give accounts, you put new accounts in your system, in your PBX for the handsets. The username is the SIM identification, and the password is the secret key on the SIM, and you're done. And they can register, and they act like normal handsets on your network. Ascosia has a beta with the patches integrated, and it works pretty well. It's kind of fun to not have to put handset information in 5 different places, and you have IVRs and voicemail and callback on busy and all these fun things automatically. So back to GSM a bit, single tower to multi-tower. The talk is big or small. So think of a tower is not really a tower. This is a tower. If you put a Raspberry Pi on this thing and give it a battery, that's a tower. So a tower is not some 40-meter lattice structure out of steel. Single tower is what we've discussed so far. Everything is in one box. All the components are in one virtual machine, and everything runs on the same host. It doesn't need to be connected to the internet. You can optimize this installation by fixing your antennas, actually, so they don't transmit into each other. You just change the planes so that they're kind of perpendicular. You can further optimize it by adding an amplifier, of course, and a duplexer on the other side so that your uplink and downlink signals don't kill each other, and basically so you don't feed back into your own radio and burn it. That's not good. Multiple towers. We take most of the components that were in the network in a box, and we stick them in something called central services. Just call it central services. You can call it your local core or whatever. The only thing running on the other towers is then OpenBTS. So they all speak back to the main central services, and you can expand your network like that. There are a lot of identity settings. I'm not going to go through all them. More abbreviations, MCC, MNC, NCC. These are color codes and identities for your logical network, for your carrier network. And these are the base station identity parameters. Which physical base station are we talking to? So they need to be coordinated in a way that lets the handset understand that these 10 physical base stations are part of one logical tower. And then you make fun things called color maps. And I'm sorry to all of the designers in the room for the next slide, but those are unique colors. So then you have this arrangement of tiles. You can look at them as tiles, as the towers that overlap with each other. They can't have the same frequency, of course, and they can't have the same color codes. So when your handset is moving around, it can very easily see different frequencies and different color codes for the base stations, but the network color is the same, and the network identity is the same. So at the bottom, keep in mind this, each tile there could represent 50 meters, something like this, with little antennas. It's about 50 meters, 100 milliwatts, or it could be 5 kilometers for each of these tiles with a bigger amplifier and nice antenna. So you have multiple physical signals, one logical network. And you actually get to support fun things like handover and mobility. Those aren't the same thing. The mobility is when you have a handset in your pocket and you're walking around and you're not on an active call, and it knows the towers that it can associate with and makes a judgment as to which one is the best signal. And then it decides by itself which tower to jump onto. Handover is when you're actually on an active call and the network is monitoring both towers. And it's saying, oh, your reception is better here, it's getting very weak here, you need to transfer your call from here to here. And that's live switchover that you don't hear, actually. You can't tell that it happens, and that's so sad because handover is so complicated to get right. The handover algorithm in OpenBTS has 40 different weights, 40 different weighting factors that tie into it about different parameters and how to tune it depending on your terrain. It's very, very, very complex. And the result for the end user is that it just works. So that's kind of sad. Roaming is just mobility among carriers. If I get in my car and drive across the border to the next country, and I have my carrier has a roaming agreement with that carrier, then I can register on their tower. You can't roam in your own network. That's impossible. APIs. We started adding APIs to OpenBTS, and this is where you can really write some software in a very short amount of time. We have one called the Physical Status API, and the output of it looks like this. It's a whole bunch of data about the raw radio reception levels, both from the network and as measured by the handset. So a GSM handset constantly tells you what it sees the network as and what neighbor towers that it sees. So you can gather information about your network layout just by moving a handset around in your city. It's like a free probe of, like a radio probe moving around. So you can take this data and do different things with it. The coolest thing by far, so far, is a company in Iceland took OpenBTS, put it on a helicopter, put another input signal for GPS, altitude, latitude, longitude, and then they fly it around really remote regions to find lost hikers because everyone has a handset with them. And this thing flies over the area and the handset sees a network and it tries to join it. So then we take all of these samples and compile them along with the three-dimensional positional data of the helicopter, and you can triangulate the person, the handset, very, very quickly. They just ran a test of this. They had someone hike out into the middle of nowhere, and they weren't told where to go. They had a 30-kilometer radius that they were searching, and they found them in 12 minutes. They used to send 100 people out in big lines and walk through these mountainous regions. So now they just fly a helicopter over. They have an iPad that keeps narrowing a circle as to where this person could be or where the signal is coming from. It's amazing. Traffic reports. One of the largest providers of congestion, like road traffic reports, is vehicular traffic, not network traffic, is cell phone carriers, because they know all the phones that are moving at 100 kilometers. They can tell how fast the phone is moving. They can tell when all of a sudden, normally in this area, people are going 80 kilometers per hour, and now they're going 20. That's a traffic jam. So they overlay that data over top of a map, and they know that the roadway is slowed down. That's actually how they get a lot of traffic report data, is from the cellular network. So you can do something like that. Automatic site survey, you can get a couple of phones, walk around your town, collect all the data, and you have your site survey done. You can model power usage. So if this is connected to a cellular or a solar panel, you can see that during this hour of the day, the most power we ever needed was this much, and the phone had this much reception. So you can automatically adjust your power on the cell tower. So this is also some visualizers I wrote for just demonstrating what kind of information is coming across here. Let me make sure my sound is off. Yeah, because I'm narrating this video. It's awful. Okay, so these are calls, again, being set up on time slot 0, then they move to time slot 1, and as the call is going, I wish I had a laser pointer, the mouse will show you in the actual MS Power, there, yes, magic mouse, right there. In the MS Power, I'm taking the handset and just moving it across my desk. And so it is telling the handset, use more power, use more power, use more power. And then I move it back across the desk, and it uses less power. And so you see when it uses more power, the signal gets better, and then the signal stays good, and it realizes it can use less power, so it moves the handset power down. You can actually drain handset batteries if you want to, just by setting one of these up. You tell all the handsets to use maximum transmission, and all the batteries will die. So yeah, you have a lot of power. So that's one of the ways we can do it. The data is being sent across like this, and it's just a WebSocket connection, actually, in the background. It's a Python script that converts our data into a WebSocket, and it keeps sending it out to the browser. Here's another visualizer. This is not based on ARFGANs, this is based on IMSIs. So you have an active call. You can, the IMSIs are the identification numbers for cell phones. It's like it's not a MAC address, but it's the identifier for the subscriber. And you can see the uplink, going down. At some point, I move the two handsets that are talking to each other. I move them apart from each other. I put my hands around one of them, just changing the reception. I take the antennas off of the radio, and you'll see all these, it grows and jumps down. And so you can see all this live. If you're watching a couple of calls, you can figure out exactly what's happening on your network. The downlink at the bottom, I'm going to put an antenna back on, and you can see it just actually jump straight up. But yeah, all of a sudden there's an antenna present, and everything got better. So we have other APIs, configuration, monitoring, version, grab all the IMSIs, whatever. So that's the next pieces. Looking ahead, this is our biggest problem. I wish I could debate a bit better in Spanish, because maybe we could figure out why spectrum is so hard to get, and why it only goes to huge carriers, and why do we have to give the huge carriers all the spectrum. Most villages, most towns, most indigenous communities only need one ARFGAN, or 2, or 3. I mean, there's 170 in each band, or 140 in each band. So you would only need to allocate 2 or 3 or 4 ARFGANs for general use in a country. And anyone in the country could then go around, put up these types of networks, connect them to the internet, and people would have service. A GSM network to put up a single tower with all the infrastructure behind it is easily $250,000. One of these can be set up with a proper antenna, proper power, RF chain, and internet backhaul, and it's like $10,000 to $20,000. Some European countries have already figured this out, and they have guard bands. They have a couple of ARFGANs that are allocated for public use at a specific power, so 100 milliwatts. You can use them in Sweden, the UK, the Netherlands. There's one more. Anyway, it's sad that there's only 3 or 4 countries in the world that do this. It's so simple. But there's a lot of money involved, so that will take a while. And this is the big thing also. Instead of giving all the spectrum to 1 or 2 people, they cut it up into smaller pieces and let smaller companies have littler slices of spectrum. It's just not saturated at all. It's sitting there empty most of the time. So what we're seeing is, it's 2014. We're seeing smartphones, tons of innovation. Everyone's becoming billionaires with applications and social media and all this other fun stuff. And it's happening between smartphones and the cloud. and the cloud, whatever that is, has a ton of innovation too, lots of services. You can jump on there and start a business. But the cellular core network is this incredibly interesting thing that hasn't changed forever because it's controlled by very few companies with a ton of money. And so the vendors, the carriers, they're all together. The service contracts for those networks, it's all major, major cash. So that's really hard to change unless we get some regulation to change the spectrum access. Then I think it will be easier. Because no matter what, it's IP. Nobody wants to build a new GSM network in 2014. And the way to maybe think about it is this is just backwards compatibility. The world used to need GSM networks and core networks that were designed very specifically, but now we have the internet. We have this amazing network. And let's think of GSM handsets as just backwards compatibility. And it's not crazy because we have DTMF in SIP, in voice over IP. I mean, it should have died. We still have DTMF and we still have fax. And we're trying to get fax and push it into new places that it does not belong at all. But we still support all these old standards or all these old ways of communicating. So why not support cellular radio interfaces as a backwards compatibility? Just say the internet should be backward compatible with these 2, 3, I don't know how many billion GSM handsets that don't cost very much money and would allow many people to have basic voice service, SMS service. You know, it's great that we're all going to have fiber optic and LTE. That's wonderful, but some people can't even call, 2 kilometers away to see if they have to go into the town today, to see if it's raining for the market, if they should show up, is it canceled, just basic time-saving things. So I think it's time for that to catch up too. That is all I have. We have a book. I forgot to promote the book last time, and I got in trouble a lot. So that book is getting published on the 8th of December, and that's awesome because it was a lot of work to write. So it's finally out. Anyway, I have time for questions.